Alright, today we're going to talk about more about the ideal gas laws. We're going to start off by talking about thermal expansion. Most materials expand when heated. For small changes in temperature, the change in length is proportional to the change in temperature. We can find or predict what that change in length is going to be by saying the change in length is equal to, and I'm still not quite sure what this Greek symbol is, this Greek symbol times L naught, which is the original length, times the change in temperature. I can tell you that little Greek symbol stands for the coefficient of linear expansion, and here is our chart for that for different materials. All right, so when it comes to calculating this change in length, we'll use our chart here for some simple materials that we'll use quite often just to get used to doing it. When it comes to area and volume, all right, because it's simply just a change in length in one direction and a change in length in another direction, we would multiply that by 2. And then when it comes to volume, it's a change in length in the width, the depth, and the height. So we would take that and multiply it by 3. Before we get much farther here, I want to make sure that, let you know that for whatever reason, I don't have the scientific reason behind it. I can just tell you what it does, is that water does not behave linearly. And this is why ice will float. And what I want you to notice here is as we start to cool water down, what we have here is temperature and the volume. And the volume, as the the temperature decreases in the water, the volume will decrease, which is what we expect up until about 5 or 4 degrees down here. And then all of a sudden, at that temperature, the volume as the temperature still decreases, the volume's increasing. So as the temperature is increasing and the volume decreases, our density is going to go down. So up until 4 degrees Celsius, all of a sudden you notice that the density starts to decrease for ice, all right, or for water, and that means that once it gets to ice, it's going to be floating because it has a density that is less than water. The why of the gas laws. Kinetic theory of gases. Gas consists of a large number of small molecules. Molecules are moving randomly. Collisions are perfectly elastic and the kinetic energy is conserved. These collisions, they exert pressure through elastic collisions with the wall. So what we're showing here is that as these collisions happen, you're going to be applying more pressure. Now, you're going to get more pressure here because the volume would not change. As long as the volume doesn't change and these things start to move faster, you're going to have more collisions, which means you're going to have more pressure. So as the temperature increases, the pressure will increase, and what we have here then is the volume stays constant. Using the kinetic theory, it can be shown that the density times the volume is equal to 1/3 the number of molecules times the mass times the velocity squared of the RMS. The mass and speed are those of an individual molecule, and what they're saying here is that the square root of v squared equals the velocity of an individual molecule. The molecular kinetic energy can be related to the temperature, and what we have here is 1/2 mv squared is equal to 3/2 K, which is the Boltzmann constant, times the temperature. The internal energy of monatomic gas is due to the kinetic energy of its atoms and is therefore related to its temperature. So they're using U here for internal energy. The number of molecules times its energy, which is going to be equal to 3/2 NKBT, which is equal to 3/2 nRT, depending on, so I think this is more of an equation that you chemistry kids would use quite often. I think you use a different term for Boltzmann constant, use an R. But in physics, what we have here is a problem. At what temperature is the average kinetic energy of the molecules of oxygen equal to 6.8 times 10 to the negative 22nd joules? What is the temperature of hydrogen molecules with that same average kinetic energy? Well, I've already got the equation written here, and I've put in the number of joules for the energy. To continue here then, we would say 3/2 in our Boltzmann constant, which is 1.38. I'm going to abbreviate here, not really abbreviate, but shorten it, times 10 to the negative 23rd times the temperature, which we don't know yet. I should use a capital T, not a lowercase t. It's not time, is equal to 6.8 times 10 to the negative 22nd. And when we solve this, we get a temperature, all right? What is the temperature of hydrogen molecules with the same, what is temperature is the average kinetic energy of the molecules of oxygen? Well, that temperature would be 32.9 Kelvin, all right? And what is the temperature of hydrogen molecules with the same kinetic energy? Well, this equation, all right, is for gas molecules. It's going to be the same, all right? You're going to get the same result. Hydrogen molecules are going to be, and I think it's actually for diatomic molecules, but you're going to get the same temperature for hydrogen molecules that you would for oxygen molecules. That's the thing about the ideal gas law, is it's going to work for all of these gases. What is the average kinetic energy of molecules of anything at room temperature of 200 kelvins? Well, let's go back. And now I'm just going to change my equation like this. And we'd solve for the kinetic energy. And when we do that, we get kinetic energy of 4.14 times 10 to the negative 21st joules. Hopefully that helped you work through that equation. Sometimes students struggle with that a little bit. Kinetic theory of gases also help us understand diffusion as a result of motion of molecules. What we have here on the left is an equal volume of O2 and CO2. And we have this porous material where there's these holes in it here. And diffusion through the barrier, what we find out is that the O2 is much easier. It's a smaller molecule. It makes it through there much easier than what the CO2 does. All right, the CO2 doesn't make it through there as easily. Let's talk more about that in class, because I don't want to spend a whole lot of time on that right now, but it's going to deal with the energy, and energy, kinetic energy, which means it's going to deal with the velocity of the materials. Let's leave it notes at that for right now, because I want to, you guys are going to get confused. We'll leave it at that. We'll talk a whole lot more about that in class. Hope that was informational. I'll catch you on the flip side.